there's one more type of vector space that is surprisingly important to have an inner product for, and that is this function space. So this C of A to B, this is our notation for the vector space of continuous real valued functions on the interval from A to B, and this is a closed interval. So how could we come up with an inner product? It seems kind of like a difficult problem at first, but what we can think about is sort of how we get an inner product on Rn, right? On Rn, you have a list of entries in your vectors, right? Here are two vectors in Rn, and to get an inner product, what we do is we sum from I equals 1 to n the product v1 u1, right? So this is the inner product on Rn. So we can use this as an inspiration for getting an inner product on the continuous functions from A to B. So what we could do is, on the interval from A to B, right, we could sprinkle some x values between A and B, and we could do this exact same kind of sum. Right? So we could do, if we have two functions f and g on this interval from A to B, then for the, let's call these x values x1 up through, I don't know, x, but we don't know how many there are, so let's say x sub k, we could do the sum from I equals 1 to k of f of x sub I times g of x sub I. Okay? Now this seems plausible at first, but the problem is that this isn't going to be positive definite, right? Because we could have a function that is 0 at all of these x values, but still not be the 0 function, right? So maybe what we should do is increase the x values, right? The problem with this is that there's so much distance between our x values, so let's increase the number of x values. How big should we make the number of x values, right? How big should we make this k? Well, really we need k to be infinitely large, because if we only have a finite number of x values, there will always be gaps between them, and that will let continuous functions wiggle around so much and, right, be 0 at all of the x values that we've chosen, but not be the 0 function. So really we want an infinite number of x values, because we kind of want to, in this product that we're adding up, we kind of want to check all of the x values. But I mean, how do you do a sum of infinitely many things when they're all, you know, possibly quite a long ways from 0? You'd get an infinite sum. So maybe what we should do is, instead of just adding them up, let's take the average of these. Right? Then we could think about taking, right, we want to let the number of x values, k, go to infinity, so we could take the limit as k goes to infinity of 1 over k times the sum of x sub I, f of x sub I times g of x sub I. But, you know, what we're starting to see here is, right, this is starting to look an awful lot like an integral, right? This is starting to look a lot like the integral from A to B of f of x times g of x. So why don't we just use this for our inner product? We don't know if it's an inner product yet, but we'll have to check. Okay, so is this symmetric? Well, yes, clearly, because if you switch f and g, nothing happens. You get the same result. Is it bilinear? Okay, so let's check. AF plus BG, inner product with H. So I say inner product. We don't know if it's an inner product yet. So this is going to be the integral from A to B of AF of x plus BG of x times h of x dx so multiplying all this mess out and shuffling things around, we get a times the integral from, oh, I shouldn't be using a here because a is the name of the left-hand end of our integral, or b for that matter. Maybe I should be using, I don't know, how about alpha and beta? So here's an alpha, here's a beta. Okay, so this is alpha here. Okay, integral from a to b of, let's see, we have f of x times h of x dx, and then the terms with betas, we have a beta integral from a to b of g of x times h of x dx, and sure enough, this is alpha times the inner product of f and h plus beta times the inner product of g and h. So this is bilinear. Okay, last one we need to check is positive definite. So let's think about what is the inner product of a function with itself. So this is going to be the integral from a to b of f of x times f of x. Okay, so this is the integral from a to b of f of x squared dx. Okay, so is this always greater than or equal to 0? Yeah, if this function inside this integral, f of x squared, because it's squared, this integrand is always greater than or equal to 0. And so when you integrate, the result is going to be greater than or equal to 0, right? Just think of it in terms of a graph. If you have a function that is always, that never dips below the x-axis between a and b, when you calculate the integral over this interval, you're only ever going to pick up positive area. You never pick up negative area, and so this integral has to be greater than or equal to 0. Okay, well now what about the last condition for positive definite, which is that the inner product of f with itself be 0 if and only if f itself is the 0 function. So is this true? Now, if with two f's is an abbreviation for if and only if. So imagine that this product of f with itself gives us 0. Well, if you have a function that's non-zero and it's continuous, right? If it's non-zero, if its square is non-zero, it has at least one x value from a to b where it's above the x-axis. But since it's continuous, remember we're working with continuous functions on this interval, since this function is continuous, if it's non-zero at this x value, it has to be non-zero on a whole interval nearby, like this. But if it's non-zero on a whole interval nearby, then the integral will be non-zero. So the only way for this integral to be 0 is for the function to be the 0 function. So yes, this is positive definite. So this formula that we've made up, this right here, is an inner product on the space of continuous functions, real valued functions, from a to b. Of course, there are other inner products on this vector space, but this is the most common inner product to use unless you have a special situation going on.